Hello everyone, my name is Farsha from University of Turku in Finland. Today I will share our work on foundation models for surface water mapping, how we make reliable map with fewer labels faster and more robustly across regions. This work grew out of the Sinking Earth Hackathon at BIDS conference and our ongoing Earth observation research. The need for accurate, timely, and global water surface mapping is crucial as it impacts numerous global applications. Surface water maps underpin flood response, drought monitoring, water resources planning, and EU policy goals such as climate adoption and biodiversity conservation. We need the methods that work quickly at scale and across season regions, often with limited label data. Historically, we relied on traditional role-based approach. These methods are simple and fast, but they have significant limitations. The most common approach is the normalized difference water index and DWI, which uses the differences between the visible and near infrared light to enhance water features. Another one is modified NDWI, uses shortwave infrared bands, which is better for distinguishing water from built-up areas and vegetations. And both result in a threshold-based mass and binary water, non-water classification. However, these rule-based maps faced some critical limitations that severely restrict their global utility. The first one, they have variable optimal threshold. The base spectral threshold is a moving target. It shifts dramatically across different geographies, season sensors types, and even illumination conditions, and making it impossible to deploy a single role globally. The second one, there are spectral confusion issues. Even if you tune the threshold perfectly, you still get confusion. For example, water bodies are frequent misclassified with snow ice or train shadows, leading to high false positive rates. And finally, they have a complex dependencies. A high quality result often required adding region-specific data like a digital elevation model, which has scalability and portability across diverse regions. This complexity naturally led us to the deep learning evolution. We saw the rise of the convolution neural networks, CNNs, which are great at capturing local texture and edge features for detailed water boundary detection. More recently, also vision transformer have emerged using self-attentions to model global context and taking the language dependencies. While these models and approach also show immense promise, their computational intensity and huge label data requirements limits their practical deployment at the continental or global scales that we need. This brings us to the foundation models. Foundation model overcome the limitations of previous methods through three key advantages. The first one is massive pre-training. The foundation model are trained on diverse massive satellite, learning rich and transferable representation from heterogeneous Earth observation data. The second one is that rapid task adoption. They can quickly adapt to the new downstream task with the minimal label data, dramatically reducing the expensive and time-consuming annotation requirements. The third one is enhanced robustness. Crucially, a foundation model maintain accuracy across varied geographic and temporal conditions, and this is the key to solving the variable threshold problem. However, despite the potential of foundation model, two main research gap remains that we set to address here. The first one is uh, the performance validation, the performance of model like Copernicus-FM on the new data set and regions outside its pre-training scope needs to be tested for environmental monitoring. And the second one is related to label efficiency quantification. We need to precisely quantify the relationship between the amount of label training data required and the resulting model performance for operational water mapping. We define two core research questions, RQ1 and RQ2. RQ1 is about the accessibility and affordability, and we would like to see how can the foundation models, I mean the Copernicus-FM, make for surface water detection more affordable and accessible, especially for the regions that needs this map most. And the second question is related to generalization. How effectively the Copernicus foundation model perform uh, when faced with the data set beyond its original training horizon. I mean, the across diverse geographic and temporal competition. And these tests the enhanced robustness claim. To answer these, we needed a challenging data set. We used the satellite images of water bodies, and this data set is crucial because it's compiled from high resolution Sentinel-2 imagery. It includes 2,841 images, each with a binary water mask, and critically, it geographically and temporally diverse, spanning multiple continents, climate zone, and a season, and covering a broad range of water types. Regarding pre-processing, it involves converting images and mass to the tensors, resizing them while preserving the aspect ratio and strictly maintaining the binary classification for the mask. Our pipeline is straightforward. Let's start with the Copernicus-FM, which is a pre-trained model on a massive approximately 18.7 million images for the from various sensors, Sentinel-1, Sentinel-2, and other sensors. The core innovation is our fine-tuning approach. We use the pre-trained Copernicus FM as a frozen backbone or encoder, and we attach a lightweight fully convolution network as a decoder. The encoder takes 3-band RGB Sentinel-2 inputs, and by freezing the backbone, we preserve the rich pre-training quality while only training a small decoder head. This means the model has only about 3.3 million trainable parameters, ensuring model light, fast, and a stable training process. Our experimental design focused on fair and transparent compression. Regarding the data partitioning, we train the lightweight decoder using varying fraction of the available training data, 10%, 20% to 100%. This tests our label efficiency hypothesis. And the second one is a compression. We ran a fair compression against a strong deep learning baseline, a unit architecture with an ImageNet pre-trained resonant 34 backbone using the same and exact same data set split and pre-processing. The third one, compressive metrics. We track everything: accuracy, parameters, count, model size, training time, and inference latency to provide a transparent cost benefits analysis for operational agencies. Table showing result for Copernicus FM on the left and the UNet 34 ImageNet on the right. The table shows a clear winner. Copernicus-FM consistently outperforms the strong Unit 34 baseline across all label fractions. At the critical 10% label mark, the unit baseline is struggling, reaching a test IOU or intersection over onion of only 0.329. And in contrast, Copernicus FM achieves a test IOU of 0.683 at just 10% of the data. The most significant performance improvement for Copernicus FM are seen in the jump from 10% to 30% and label data, demonstrating that even a minimal investment in annotation yields and give us the massive returns. The differences in IO is consistently over 0.35 at every fraction. And this confirms the foundation model, computation foundation model, reduced the annotation requirements, making high quality water mapping accessible and affordable for resource constrained regions. And the table showing training details, parameters counts for both models. On the left side, the Copernicus FM, and on the right side, the Unit 34. And now the foundation model setup fine-tunes a decoder with only about 30.3 million parameters, resulting in tiny on-disk model size of about 30 megabyte. Sorry. And in contrast, the unit resonant 34 baseline has over 24 million trainable parameters, and the model size approximately 93 megabytes. And it's clear that foundation model approach delivers superior accuracy while requiring the model that is 7 times smaller and has a 7 times fewer trainable parameters than the unit. And this high performance combined with the minimal computational costs firmly answer research question number 2 by demonstrating the robustness and transferability of Copernicus FM features to the new diverse task. Regarding the qualitative result, also support our findings. The predicted mass delineate water bodies cleanly, even at the low-level fractions. Typical errors are concentrated along the shorelines and small inlets, which is expected. However, the qualitative quality improved rapidly between the 10% to 30% label fraction. And then the differences between the 30% and 100% are quite subtle. And to summarize, our study makes 4 key contributions to the Earth observation community. That's the first one is the systematic evaluation. We provide the first comprehensive assessment of Copernicus FM for surface water segmentation on external diverse dataset, demonstrating its impressive feature transferability for environmental monitoring. The second one is label efficiency curves. We have quantified the performance across 5 label fractions, clearly showing when returns saturate and minimum annotation is needed for operational quality. And number 3 is transparent cost analysis. We offer a complete resource accounting, including computational costs, making this a reliable and actionable solution for agencies with a limited budgets. And the last one is a scalable framework. Is our fine-tuning approach provides a adaptable, efficient, and scalable solutions for analyzing new regions and inputs, supporting diverse remote sensing research and operational deployments. And thank you so much for your time and attention. I believe the foundation model, especially Copernicus foundation model, represent the future of accessible high performance Earth observation. And I'm happy to take any question you may have. Please feel free to reach out to me via email. Thank you so much and bye.